Hi guys. Today we will learn about logic gates. First, you have to know your most essential learning competency for this lesson, which is to demonstrate how each logic gate operates. And these are your specific objectives. Define logic gates. Enumerate the different logic gates. Identify the Boolean expression of each logic gate. Complete the truth table of each logic gate. Determine the logic output of a combination of logic gates. And establish the truth table for a combination of logic gates. Digital devices work on ones and zeros. Integrated circuits interpret and process these digital input signals, allowing the device to interact with its users, the humans. Now let's proceed to our lesson proper. What is a logic gate? A logic gate is a circuit whose output voltage level depends on the logic rules applied to its inputs. The logic inputs are labeled A and B. The logic output is labeled either X, Y, Z, or sometimes Q. The logic inputs and outputs are ones and zeros. 1 means high voltage level or on. 0, on the other hand, means low voltage level or off. Here is a practical example of a logic gate package. It contains 4 logic gates, but of one kind only. Logic gates or simply gates are of many types. We can classify them as principal or basic gates, which are the AND gate, OR gate, and NOT gate. There are also universal gates, which are the NAND and OR gate. Lastly, there are other logic gates which are combinations of the basic gates. These are the exclusive OR gate, exclusive NOR gate, negative AND gate, negative OR gate, and digital buffer gate. This last classification also includes the special output gates, which are the complementary logic gates. Now watch this short clip of an AND gate. Observe the input indicators on the left and output indicator on the right. If the LED is on, that means 1. If is not lit up, that means 0. These combinations will be summarized in a truth table. Here, the inputs are both 0. This combination yields an output of 0. If input A is 1 and B is 0, the output is 0. The output is also 0 if input A is 0 and B is 1. But if both A and B are 1, the output Y is 1. This is the truth table of the AND gate, summarizing the different input combinations we had just demonstrated. The Boolean expression on the right, y equals A dot B, can be read as A and B gives Y. And this is the block diagram of AND gate. Next is the OR gate. Observe again the input and output indicators. You can pause after this clip and try to construct its truth table. This is the OR gate truth table. Did you get it right? The Boolean expression, y equals A plus B, can be read as A or B gives Y. And here is the block diagram of OR gate. Make sure to memorize the block diagrams. This is the last principal gate, the NOT gate. You can pause after this clip and construct its truth table. Notice that NOT gate has only one logic input. This is how simple the truth table of NOT gate. Did you get it right? The Boolean expression of NOT gate can be read as y is not a, or the inverse of a is y. In some references, the complement of a is denoted as a naught or a bar. Aside from bar, a prime symbol is also used. And this will be read as a prime. Remember the bubble in that block diagram. We don't have a video for the digital buffer gate because the device doesn't have it. But for you to easily remember it, the NOT gate is simply the opposite of digital buffer. This is why the NOT gate is called the inverter. Here in this buffer gate, the output is also the input. Notice that the buffer gate symbol has no bubble. Buffers can be used for power amplification of a digital signal as they have what is called a high fan-out capability. Now let's observe our first universal gate. The NAND gate. You can pause after this clip and construct its truth table. Here is the NAND gate truth table. Did you get it right? The Boolean expression of NAND gate is read as A and B gives not Y. This means that the NAND outputs are the complements of AND gate outputs. NAND gate is simply the combination of AND NOT gate. So the block diagram is an AND gate with an inversion bubble. The second and last universal gate is the NOR gate. You can pause after this clip and construct its truth table. Here is the NOR truth table. Did you get it right? Its Boolean expression is read as A or B gives not Y. The NOR gate is the combination of OR and NOT gate. Thus, its block symbol is an OR gate with inversion bubble. We already tackled one of the other gates, which is the buffer gate. The other gates are combinations of two or more basic gates. In the case of the buffer gate, it's the combination of two NOT gates. Here is a clip of exclusive OR gate, which is a combination of several principal gates. You may pause after this clip and construct its truth table. Here is the truth table of exclusive OR gate. Did you get it right? Notice that, to get an output of 1, the inputs must not be the same. The Boolean expression of exclusive OR gate can be read as A or B but not both, gives Y. And here is the block symbol of exclusive OR gate. It is like OR gate, but with extra curve line. Here are some possible ways to construct the exclusive OR gate. The third diagram below shows an exclusive OR gate made of NAND gates only. This is the reason why NAND gate is a universal gate. We are almost done. Here is a clip of the exclusive NOR gate. There is no exclusive NOR gate here in our device, but we can get the right outputs by adding NOT gate to the exclusive OR gate. You may pause after this clip and construct the truth table. Here is the exclusive NOR gate truth table. Did you get it right? Notice that, to get an output of 1, the two inputs must be the same, whether both 1 or both 0. The Boolean expression is read as, if A and B are the same, gives Y. The block symbol is simply an exclusive OR gate with inversion bubble. Just like the exclusive OR gate, XNOR can also be constructed by several other gates. A negative AND gate functions the same as an AND gate with all its inputs inverted. In keeping with standard gate symbol convention, these inverted inputs are signified by bubbles. Contrary to most people's first instinct, the logical behavior of a negative AND gate is not the same as an AND gate. Its truth table, actually, is identical to an OR gate. Following the same pattern, a negative OR gate functions the same as an OR gate with all its inputs inverted. In keeping with standard gate symbol convention, these inverted inputs are signified by bubbles. The behavior and truth table of a negative OR gate is the same as for an AND gate. It is sometimes desirable to have a logic gate that provides both inverted and non-inverted outputs. For example, a single input gate that is both a buffer and an inverter, with a separate output terminal for each function. Or, a two-input gate that provides both the AND and the NAND functions in a single circuit. Such gates do exist, and they are referred to as complementary output gates. Complementary gates are especially useful in crowded circuits where there may not be enough physical room to mount the additional integrated circuit chips necessary to provide both inverted and non-inverted outputs using standard gates and additional inverters. They are also useful in applications where a complementary output is necessary from a gate, but the addition of an inverter would introduce an unwanted time lag in the inverted output relative to the non-inverted output. That's the end of our discussion. Now you can check if you have learned something. You may pause the video before each test reveals the answers. Thank you for watching.